Okay, in this presentation we are going to look at a worked example from Introduction to Probability, essentially. So this worked example is specifically relevant to computer science and computer science students. So here we have our scenario, a binary channel, okay. The frequency of a zero signal to a binary channel is 0.6. If the 0 is the input, then 0 is the output with a probability of 0.8. So we have an input signal and an output signal. And let's just read the next line here. If 1 is the input, then the output is 1 with a probability of 0.9. Okay, input signal that can either be 0 or 1, and an output signal that can be either 0 or 1. And so there's a little bit of problem in that this suggests that if 0 is the input, then 1 might be the output with a probability of 0.2. That's coming from the second bullet point. Okay, anyway, so let's just look at the questions here. Calculate the probability that the output is 1. Calculate the probability that the output is 0. Calculate the probability that the input is 1 given that the output is 1. Calculate the probability that the input is 0 given that the output is 0. Okay. So what I'm going to do here is just use the notation, the terminology IS, input signal and output signal. Because if I just use I and O for output signal, and when we have zeros and ones, it'll get very confusing very fast. So IS, OS is input signal and output signal. Okay. So the probability that the input signal is 0 is the probability IS equals 0, and that is 0.6. And necessarily, the probability that the input signal is 1 given is necessarily 0.4. Okay, that's just the complement rule. Okay, we're told that in our scenario. Now, these are the conditional probabilities that we've been told, and the two of them we can imply based on the pieces of information we are given. So the conditional probabilities, probability of OS, output signal, equals 0, given that IS, input signal, equals 0, equals 0.8. Okay, now we're going to use the complement rule for the second bullet point. Probability of OS equal 1, given IS equals 0 equals 0.2. Okay, because those probabilities must add up to 1. And the third bullet point, probability of OS equal 1 given IS equal 1 equals 0.9. That's what we are told. And necessarily the probability of OS equals 0 given IS equal 1 equals 0.1. So 0.8 plus 0.2, they add up to 1. 0.9 plus 0.1, that adds up to 1. Okay. Now for exercise 1, and I'm going to spend most of my time with this one here because this sort of explains, this is where we do most of the hard work, and we'll be using a lot of results subsequent to this in future exercises. Calculate the probability that the output is 1. So what we have to do here is use the total probability law. The total probability that the output is 1, probability of OS equal to 1, can be calculated using the law of total probability. So probability of OS equal to 1 equals the probability of OS equal to 1 and IS equal to 1 plus probability of OS equal to 1 and IS equal to 0. Okay, so there's two ways we can get an output signal of 1. If the input signal is 1, okay, and the output signal is 1, everything's working fine. But if the input signal is 0 and we get an output signal of 1, that's still relevant in this case, basically. Okay, so it's essentially the combination of those two events. So what we have to do is use the conditional probability law, rearrange that to actually get an expression for those joint probabilities in terms of the conditional probability and the probability of the input signal being 1 and 0. Okay, so these pieces of information here are what we have. Okay, so we have both of those together, and so essentially what we're going to do is use all those pieces of information, multiply them out, and that will help us get the answer we're looking for. Okay. So the probability of OS equal 1 and IS equal to 1 is probability OS equal to 1 given the probability of IS equal to 1 times the probability of IS equal to 1. Just to emphasize it, that's the conditional probability formula just rearranged. And likewise, for the second bullet point there, similarly, that's the conditional probability formula just rearranged. Okay? So essentially what we're going to do now is update our formula. Probability of OS equal to 1 equal to the probability of OS equal to 1 given IS equal to 1, IS equal to 0, times the probability IS equal to 0, plus the probability of OS equal to 1 given IS equal to 1 times the probability of IS equal to 1. Okay, so we have it up there, and that is 0.2, which is this part here. Whoops, went a bit too far there. No, here. That's 0.2 times 0.6 plus 0.9 times 0.4. Okay, so that's four clauses there, four elements of that expression. 0.2 times 0.6 plus 0.9 times 0.4. And that is equal to 0.12 plus 0.36, which is 0.48. So the total the probability the output is 1 is 48%, 0.48. Now, calculate the probability of the output being 0. Essentially, it's more or less the same here. So I'm just going to be a bit quicker about it. We have the same sort of setup there. We have used the laws of total probability, rearrange the probability of OS equal to 0 and IS equal to 0 using the conditional probability formula into the terms we know there. Likewise, probability of OS equal to 0 given IS equal to 1, IS equals to 1, IS equal to 1 times the probability of IS equal to 1. Okay. So it's the same sort of approach there. Anyway, so that is 0.8 times 0.6 plus 0.1 times 0.4. And that is 0.48 plus 0.04, and that is 0.52. So the probability that the output is 0 is 52%. And if you think about it, that is complement of this here. Okay, so we can only have two outputs, 0 and 1. So this is 48%. This has to be 52%. Okay, which is actually a perfectly fine way of specifying that answer. It's perfectly justifiable just to use the result in exercise A. Anyway, we'll keep going. Calculate the probability that the input is 1 given that the output is 1. Okay, so what we need to do is calculate the probability of IS equal to 1 given that the OS is equal to 1. Okay, so what we're going to do here is use the Bayes theorem, and essentially this is the probability of IS equal to 1 given OS equal to 1. That can be written as the probability OS equal 1 and OS equal to 1. Okay, but what we can do there is just use this expression here. This is just the Bayes theorem essentially. This is, in case you're wondering, it's just a conditional probability used twice essentially. Okay, so that is equal to the probability of OS equal 1 given IS equal to 1 times the probability of IS equal to 1 divided by the probability of OS equal to 1. Okay, so we have all those values before. Okay, we found previously that the probability of OS equal to 1 given IS equal to 1 times times the probability of IS equal to 1. That's something we've used already in previous questions. That was 0.9 times 0.4. Okay, that's the numerator. The denominator we have found in exercise A. That's the probability OS equal to 1, and that is 0.48. Okay, so it's 0.36 divided by 0.48, and it is 75%, 0.75. And likewise, exercise D, calculate the probability that the input is 0 given that the output is 0. So what we have to do here is calculate IS equals 0 given OS equals 0. And again, we use Bayes' theorem. So that is as follows. The numerator is the probability of OS equals 0 given IS equals 0 times the probability of IS equals 0 divided by OS equals 0. Okay? And again, we're using a lot of numbers that we've calculated already. We were given 0.8 and 0.6 as the conditional probability and the probability of the input signal being 0 as 0.6. In exercise B, we found out that the probability of OS equals 0 is 0.52. So essentially what we have there is 0.48 divided by 0.52, and that is approximately 92%, 0.923. So the probability that the input is 0 given that the output is 0 is approximately 0.923, 92.3%. Okay, we'll leave it there.